All right, let's get started. The exercise we study today is the stochastic version of the one-sector model of optimal growth. In other words, the stochastic version of the neoclassical, the basic neoclassical growth model. The difference to the deterministic case is that we have a multiplicatively added stochastic noise to the one period return function. The basis of the utility function is consumption, which is defined in this way. This is production with the stochastic noise. So xt stands for the capital stock, zt is the stochastic noise, and this is the last term on the right is the capital stock next period. So the one period return function is based on the utility function with consumption as its variable. So this is the one period return function. First, we need to formalize the sequential problem. So this is what we want to do, where E is the expectation operator. So this is what we want to solve to find a path for the capital stock that attains the supremum in this sequential problem. We have a number of assumptions regarding the functions, the utility function, the production function, as described in the problem, which you can find in the textbook. So here we don't need to rewrite these assumptions. We just use them. First, in problem A, we are supposed to describe the feasible plans for this sequential problem. First of all, we need to find the feasibility set gamma. This is the correspondence gamma. It's easy because next period's capital stock cannot be lower than 0, and it cannot be higher than total output in period t. So this is the feasibility set. So using this feasibility set, the sequential problem, I'm trying to expand the problem without the summation. So it's an infinite sum based on the optimal plan. Yep. And the third term and the like until infinity, which in short can be described as an infinite sum. So these two formulations are completely equivalent, starting with 0 and going to infinity. All right. To calculate the expected value of the value, we need a probability measure. The shock is i.i.d. So in this case, we have this probability measure for the shock history. This is an easy feat, okay, because period t shock is completely independent of the previous shocks. So thinking in terms of the value of plans, we will use this infinite sum. First, I will give the expansion, then we will summarize. Okay, so now we can calculate the expected value with respect to the probability measure we have just created by using the fact that the shock is i.i.d. and in short, we can use this very brief formulation. Okay. And that's the solution to problem A. Please refer to page 2, not 24, 44. Page 244. There we studied how to calculate the value of a plan. And there we calculated the expected value of the one period return function by integrating the function with respect to mu t, the probability measure. So here we did the same. We calculated the value of plans. So we were thinking in terms of the stuff covered on page 244. So supremum, the supremum is the supremum of plans. So this is the reason why we formalize the problem in this way. When we calculate the supremum, we calculate the supremum of plans. All right. The next problem under problem A is to describe the feasible plans. So let's see what we know. This is consumption on the basis of which we calculate utility for every period. We also know that consumption cannot be zero, and we also know that next period capital stock cannot be higher than total output in period t. So given the fact that next period capital stock cannot be zero either, just like consumption, we have the following relation. Okay. So investment must be non-negative. So we have just ensured with these relations that next period's capital stock, period T investment, must be in the feasibility set for every period. Okay, so we can give the set of feasible plans, by declaring that for every T, decisions must be in the feasibility set. Okay, so that's all to problem A. In problem B, we need to show that there exists a unique bounded continuous function V satisfying the functional equation or the Bellman equation, and that the related optimal policy correspondence G is non-empty, compact valued, and upper hemi-continuous. So as a first step, let's write the Bellman equation of the problem. We are looking for the maximum of the function, supposing that the optimum choice is in the feasible set or feasibility set. This is the one period return function. This is the function of x, y, z. And this is the expected value of the value function, yet unknown value function, which we calculate with an integration with respect to the probability measure of the i.i.d. shock. So we have a number of assumptions regarding the production function. Assumptions T1, T2, T3, and T4 describe the basic assumptions. On the basis of these assumptions, we can state that there is a unique maximum capital stock that satisfies this equation. Actually, this is a fixed point where Z upper bar is the maximum value of the shock. So on this basis, we can find that the state space for the endogenous state variable is a closed interval. So this is this state space for the endogenous state variable. Given that we need to show that there is a unique bounded continuous function V, value function, satisfying the Bellman equation, we should play on theorem 9.6, because theorem 9.6 describes the prerequisites that are needed for a unique bounded continuous value function satisfying the Bellman equation. So just a kind reminder, just like in the deterministic case, here in the stochastic case we will do the same. We will utilize the fact that an unbounded return function, and here we have an unbounded return function, so an unbounded return function can be made bounded by forcing its variables to closed intervals. So even if, in other words, even if the one period return function is unbounded, it's gonna be bounded if all the state variables move on closed intervals, just like in this case. So the strategy we are following here is to check if the assumptions underlying theorem 9.6 are satisfied or not. So assumption 9.4, X, the state space, is a convex Borel set, since we have this closed interval for the endogenous state space. This is a convex Borel set. So assumption 9.4 holds. Assumption 9.5, shock variable is continuous in this case, so assumption 9.5b is active in this case. This is the state space for the exogenous. This is supposed to be 1. So this is the state space for the exogenous state variable, which is convex and compact and the Borel set. So assumption 9.5 is satisfied. This is great. The next question is whether this probability measure has the failure property or not. Please refer to page 213 and page 220. In this case, using the language of the referred pages, we have the Markov operator for the problem. So this is our probability measure belonging to the i.i.d. shock. Given the fact that probability measure lambda, it is a probability measure, so it is continuous and bounded. So integrating function f with respect to this probability measure leads to continuous and bounded functions if function f is continuous and bounded. So if function f is continuous and bounded, integrating the function with respect to the probability measure leads to bounded and continuous functions. So the probability measure we have has the failure property. So assumption 9.5 is satisfied. The next assumption is 9.6. It has 3 parts. First, gamma is non-empty. Gamma is non-empty because we have this correspondence, which is non-empty because in the worst case 0 is in the set, so it cannot be non-empty. This is great. Gamma is compact valued, which is also satisfied because gamma, for every x and z, gamma is a closed interval, so it is compact. This is the short answer. Intuitively, we can say that for any z and x, correspondence gamma has no holes, and every inner processes, convergence processes, has the limit point, has its limit point in the interval, in the set. So yes, gamma is compact valued, and gamma is continuous because its lower bound is 0, which is continuous for every x and z, and the upper bound is given by the function given by a continuous function, because it is continuous because f is continuous, and the continuity of f is ensured by assumption t1 in the problem. So gamma as a correspondence is given by two continuous functions. Its lower bound is a continuous function, its upper bound is a continuous function. So gamma is continuous, just like in the deterministic case, where we saw that if a correspondence gamma is given by two continuous functions, correspondence gamma is continuous. So assumption 9.6 is satisfied. The next assumption is assumption 9.7. It has two conditions. The one period return function f must be bounded and continuous, and the discount factor must be in the open interval 0, 1. The latter condition is satisfied by assumption u1. You can check it in the text of the exercise. One period return function f, in this case, is given by a composite function, an inner function, the composition of an inner and an outside function, in which this relation holds. Continuity of the one period return function follows from the continuity of utility function u and the continuity of production function fx, and these conditions are satisfied by assumptions u2 and t1. So this is continuity. Boundedness follows from the fact that state variables are forced into closed intervals. So given the fact that state space for the endogenous and for the exogenous state are closed intervals, so both state variables move on closed intervals, one period return function is bounded and continuous. So assumption 9.7 holds. On this basis, we can say that theorem 9.6 ensures that there is a continuous and bounded fixed point, which is a return function v, and the policy correspondence G, capital G, belonging to the Bellman equation is non-empty, compact valued, and upper hemi-continuous. Okay, exercise, this is just a reminder, exercise 9.6, according to exercise 9.6, under assumptions for 9.4, 5, 6, and 7, assumptions 9.1, 2, 3 are satisfied. So under assumptions 9.4 up to 9.7, theorem 9.2 works. So the solution to the Bellman equation is the same as the solution. So this is the same solution as the solution of the supremum, solution of the sequential problem, and theorem 9.4 also works. So the plan that satisfies, that attains the supremum in the sequential problem is optimal in terms of the Bellman equation. So thanks to the assumptions, these two theorems work, and these two theorems together, they ensure that solutions to the sequential problem and the Bellman equation coincide both in terms of the value function and the optimum policy. This was problem B. In part C of the problem, we are supposed to show that value function v is strictly increasing and strictly concave in its first argument, and that the related policy function, policy correspondence g, is a continuous single-valued function. So we need to show that we have a unique continuous policy function. Monotonicity of value function v is ensured by theorem 9.7. So we need to play on theorem 9.7 and to check if the underlying conditions are hold. In addition to the assumptions we have already checked, we need assumption 9.8 and 9.9. So we need to check now. We need to check if assumptions 9.8 and 9.9 are satisfied. Okay, so let's start with assumption 9.8 with given y and z. We need to show that the one period return function given by this formula is strictly increasing. We know that the one period return function can be described in this way, so we should use this form. Assumption u3 and assumption t3 together ensure that the inner function and the outside function is strictly increasing. So on this basis, a one period return function f is strictly increasing in x. So yes, we can say that one period return function f is strictly increasing in its first argument x. Assumption 9.9, for every z that comes from the state space of the exogenous state, correspondence is increasing in the sense that if x is not higher than x prime, implies that correspondence for x and z is a subset of the correspondence at x prime and z. In this problem we are dealing with, it follows, this fact follows from the basic characteristic of the production function, which is strictly increasing. Let's see how to demonstrate the monotonicity of the correspondence in this case. This is a well-known fact in this problem, so we can describe, and we describe the correspondence, the feasibility set in this way. If x is not higher than x prime, then for any given z, this relation holds. So this is an easy feat. It's no big deal to realize that gamma, correspondence gamma, is monotone in the required sense. So assumptions 9.8 and 9.9 are satisfied. The concavity, so we can say, at this point, we can say that policy function v is strictly increasing in its first argument. The next problem is the concavity of the same function, the value function v. To demonstrate the strict concavity of the value function, we need to refer to theorem 9.8. So we are going to do the same. We need theorem 9.8 to ensure that the value function is strictly concave. So the only thing we need to do is to show that assumptions 9.10 and 9.11 are satisfied. These assumptions are underlying theorem 9.8. So assumption 9.10 is about the concavity of the one period return function for any given exogenous shock. We need to calculate the Hessian. This is the way I have chosen for the solution. So we need to calculate, we need to build the Hessian matrix for the one period return function. Okay, so once again, this is the function we are working with. No. Oh geez. This is all I need to do. So this is the function we are using. So we will find the Hessian matrix for this function. Okay, so let's go step by step. It's a very nice exercise, so let me show you only the solutions to the partial derivations. So this is the first derivative of the one-period return function with respect to the first variable. This is the first term in the Hessian. I am trying to be as precise as I can. Okay, we don't need this. No. It works. This is the second term in the Hessian. I am simplifying, okay? This is positive. This is positive. All right. This is the first derivative with respect to the second variable in the one-period return function. So describing the partial derivative as simply as I can. So please realize that they are the same as we expected. And the last term in the Hessian is this function. So we need two conditions. Okay, so these are the building blocks for the Hessian. To be strictly concave, the one-period return function must satisfy two conditions. This is okay. So this is satisfied. And the Hessian, this is negative. This is positive. Of course, it is positive. And it is negative. Okay. We have a result. We cannot say it's supposed to be positive, but we cannot say on the basis of the signs that it is positive. So we need to do the calculations. The calculations are the following. Okay. Yep. Yep. It's gonna be simpler in the end, I promise. In the end, it's gonna be very simple. First, we just need to struggle through the operations, the manipulations. Yep. And in the end, okay, and this is positive. So the Hessian is positive. So we can say that that assumption 9.10 is satisfied because f is strictly concave. Strictly concave. All right. Assumption is gonna be exciting, I promise. Assumption 9.11. If y is in the correspondence and if y prime is in the correspondence belonging to x prime and z, then the weighted average of the points must be in the correspondence belonging to the weighted average of x and x prime with given x. All right. It means, so what does it mean? It means it's the same thing expressed in a different way. It means that the weighted average of the points falls into this interval. Okay, so I am just translating the conditions into a form which is more useful for our current purposes. The facts. Let's see the facts. There are two things we know for sure. This is one thing, and this is the other thing, which comes from the fact that y and y prime, both points are in the related correspondence sets. It follows that this relation also holds, and there is a pair for this relation in the other case. It follows, if we add up these two relations, inequalities, then it is also true. It also holds. It is starting to look like something we need, but trust me, it's not the thing we need. Here we should realize that the right hand side is the weighted average of 2 points, and here, building on the strict concavity of the production function, we can realize that the right hand side of the inequality we are dealing with, so by building on the strict concavity of the production function, we have this relation, and this is something which is very useful for us, because it means that the weighted average of the optimum decisions lies in the in the correspondence belonging to the weighted average of x and x prime. And this is what we were supposed to show. So assumption 9.11 holds, because both assumption 9.10 and 9.11 hold, theorem 9.8 works, and it ensures that value function v is strictly concave, policy correspondence capital G is continuous and single valued, so it can be referred to as policy function G. In part D of the problem, we are dealing with the policy function. We are examining the monotonicity of the policy function in its variables. So we have this policy function which has two variables, the two state variables, and we need to show that it is increasing in both its variables. So strictly speaking, briefly speaking, we want to characterize the policy function as strictly as possible. So let's start with the first order condition of the problem that comes from the Bellman equation. So this is the first order condition. I'm sure you are familiar with how to get to the first order condition of a Bellman equation. The decision variable is y, so we derive the Bellman equation with respect to the variable y, and that's all. So with the given x and z, two sides of this equation, the first order condition, can be charted in a figure as the function of y. What we know and what we should use are the facts that value function v is strictly increasing and strictly concave, and utility function is strictly increasing and strictly concave. So let's try to set up a simple figure in which we chart the two sides of the first order condition as the function of y for any given z and x. Given the fact that the shock is i.i.d, we can use this simplified version of the right hand side. So we don't need the integral. We can use the expectation operator. In this point, we have a unique choice as the equilibrium of the two sides, and this is the policy function, the output of the policy function with the given x and z. If we increase x with a given y, if we increase x with a given y, fx, the production function, gets higher due to the monotonicity of f. F, the production function, is strictly increasing in x. So the utility function is lowered because of the concavity, of the utility function. Yep. So this is the higher x that shifts the left-hand side of the equation to the right, and you can see here we have a higher optimum choice. So intuitively we can say that the policy function g is increasing in x, but we want to find a formal way in which we can demonstrate that policy function g is increasing in x, plus policy function g is increasing in z. How to do this? Let's assume that policy function g is strictly decreasing in x, and try to find a contradiction. Let's try to find a contradiction. So x dot, let's assume that x dot is higher than x. In this case, then we have the following relation. So we are using the policy function g, which now is supposed to be strictly decreasing in x. On the other side, on the other hand, let's put the other x into the utility function, and given that f is strictly increasing in x, and given that policy function g is supposed to be strictly decreasing in x, then on the right the argument of u prime is higher than the argument on the left, so this relation holds. From the first order condition, it follows that using this relation, we can say that it is equal to the value function. This is what follows from the first order condition, and it also holds. So by using the first order condition, we can relate the value function at the different endogenous state, different values of the endogenous state variable. From this, it follows, by using the relation between the marginal utility function this is the immediate consequence of the relation between the marginal utility functions. Okay. Given the fact that we have already demonstrated that value function v is strictly increasing and strictly concave from this latter relation, it follows by using the concavity of the value function, this relation follows, which is a contradiction because we assumed that g, policy function g, is strictly decreasing in x. We arrived at a contradiction, so we infer that g, policy function g, is increasing in x. In the same way, we can demonstrate that policy function g is increasing in z. Let's assume that policy function g is strictly decreasing. Strictly decreasing in z. Let's use the marginal utility function. And let's play on the same contradiction. Or if not the same, a very similar contradiction. Now, we have two distinct values for the exogenous shock, and by putting these shocks into the marginal utility function, we have the following relation. Just because this part of the argument has increased, this part of the argument has decreased on the basis of the assumption that policy function g is strictly decreasing in z. From the first order condition, it follows that we have a relation regarding the marginal utility functions and by using the concavity, strict concavity of the value function, which we have already demonstrated, we receive this relation, which is a contradiction. So, given the fact that on the basis of our assumption we arrived at a contradiction, it follows that the assumption cannot be true. So policy function g is increasing in z. Okay, so we have just demonstrated that policy function g is increasing in x and z in both of its arguments. We want to characterize as strictly as possible the consumption function, even though we haven't touched upon the problem of a consumption function. We have a consumption function because consumption lies between output and investment. So as the difference between output and investment, we can express the consumption function. So we want to show that consumption function is increasing in x. So assume the consumption function is strictly decreasing in x, and let x dot be higher than x. Now we can state the following. Please be aware of the fact that it is consumption that is the argument of the utility function, and now that we have an explicit consumption function, we can use this function as the input of the utility function, marginal utility function, given the assumption that the consumption function is strictly decreasing in x. We have this relation, and from the first order condition, it follows that marginal utility is equal to the expected value function at x and it also holds. Please don't forget the fact that the value function has two variables, and from this fact it follows and given that the shock is i.i.d, we don't need to pay attention to z prime. It's completely unrelated to the current shock and current endogenous state. So it's no problem. From this fact, it follows that we have this relation. No. So we have this relation, and with some manipulation, we receive this relation, which is positive because f is strictly increasing in x. So everything is positive here. And with some manipulation, we can state, actually no manipulation is needed, we can claim this relation immediately. Which is a contradiction. So in contrast with the assumption we made in the beginning, consumption function C is increasing in X. What can we say about the monotonicity of the consumption function in its second variable? We can demonstrate that consumption function C is increasing in Z in the same way. Let's assume that consumption function C is strictly decreasing in Z, and let Z dot be higher than Z. Now, by turning to the marginal utility function, we can say that this relation holds because we have just assumed that consumption function is strictly decreasing in Z. From the first order condition, it follows that this relation holds, and from this it follows. It's a very useful relation because we can say that it is true, it holds. Given that Z prime, not prime, dot, sorry, is higher than Z, it is positive, and it is also positive. So it follows immediately. No. And finally, we receive that the consumption function is higher at higher values of the exogenous state. This is a contradiction. So we received that policy function, it's not the policy function, consumption function is increasing in its second argument too. That's all. In section F of the problem, we replace a previous assumption. Instead of Z2, assumption Z2, according to which the shock was i.i.d, now we have assumption Z3, according to which we have a transition function Q having the failure property. So in this way, now we have a first order Markov process for the shock variable. The Bellman equation of the problem is modified because now we have a different shock process. It looks pretty similar to the Bellman equation of the previous case, but instead of the i.i.d shock, now we use this new shock with the transition function, and we are supposed to check if the previous results hold. Most importantly, results regarding the monotonicity of the policy function g cannot always be demonstrated. So In other words, some results of the previous case are going to be changed under this new assumption. So I'm trying to set up a similar figure for this case. So we can do the same. We can chart the two sides of the first order condition as the function of y for any given x and z, and given that the shock is not i.i.d, we should use the transition function for accuracy. Any change in x works in the same way as it worked previously. So policy function g is increasing in x, but any change in z now works through the transition function q. So any change in z may affect the expected value of the value function, but the directions of this change are unknown because we don't have enough information. We don't have all the necessary pieces of information regarding the transition function. So on the basis of the assumptions of problem F, we cannot say that policy function g is increasing in z while it is still increasing in x. The value function is increasing in z is ensured by theorem 9.11, and in order that we can use theorem 9.11, we need assumptions 9.13, 14, and 15. So let's check if these assumptions hold. Assumption 9.13, one period return function described in this way is strictly increasing in z because of utility function u is strictly increasing. So assumption 9.13 holds. It's okay. Assumption 9.14, for any given x coming from the state space, gamma, the correspondence gamma is increasing in the sense that given two shocks, this relation is supposed to hold. So the correspondence for a lower exogenous state must be a subset of the correspondence gamma at the higher shock variable. Given the fact that it's pretty easy to describe the correspondence in our case, it's no big deal to realize that if z prime is equal to or higher than z, then the correspondence is really a subset of the correspondence at the higher shock. So assumption 9.14 holds, and assumption 9.15, transition function Q is supposed to be monotone, which means if we have a function f which is increasing, if a function f is increasing, then the expected value of this function calculated with an integral with respect to the transition function must also be increasing. So given that assumptions 9.13, 14 and 15 hold, then according to theorem 9.11, transition function v is increasing in z. As I have just mentioned that policy function g is still increasing in x, we want to know something about the monotonicity of the policy function with respect to z. At this point, we need to use the monotonicity of Q, which is ensured by assumption 9.15. So let's have this relation. So we have two shock variables, and let's use the concavity of U prime, I mean the marginal utility function. We have the policy function, and we assume that G is strictly decreasing in Z, just like previously. So this is the reason why this relation holds. From this fact, it follows, thanks to the monotonicity of the transition function, from this it follows that at the higher value of the exogenous state, the policy function is higher, which is a contradiction. So G, the policy function G, is increasing in Z. Please note that this relation was key in the proof, which comes from the first order condition, from the fact that transition function Q is monotone. We can build on the fact that the two sides of the first order condition behave in the same way. So if this relation holds on the left hand side, the same relation must hold on the right hand side, just because of the monotonicity of the transition function Q. That's all.